Welcome. My name is Evan Yang, and I'm a senior in the Math Science Technology Center at Dunbar. Today, I will be presenting to you about my research project. I've spent the last 2 years working on this under the mentorship of Yang Song. My project is about developing pipelines to automatically map road assets. Here's an outline of today's presentation. First, I will be going over the background and the purpose of this project. Then I'll be discussing my methodology and results. Next, I'll address future work to be done in this field. And finally, I'll open the floor up for questions. First, road asset maps are maps of road assets. Road assets are pieces of infrastructure that help improve the safety and quality of our roads, such as signs, traffic lights, or barriers. These maps are needed to maintain and keep inventory of road assets. The Kentucky Transportation Cabinet has been working to find methods to effectively create up-to-date and accurate maps of these road assets, which is where my project comes in. My project involved using machine learning models to help efficiently map road assets. Machine learning is a new idea in computer science that involves algorithms that learn and improve from experience without explicitly being programmed to. However, in order to do so, machine learning requires a large data set from which the model can train on. So the purpose of my project was to demonstrate efficient methods to create maps of road assets. My methodology was to develop pipelines to create maps. This pipeline had 3 segments: an image generation part, an image classification part, and a map creation segment. The pipeline was applied to guardrails and stop signs. The purpose of the image generation part was to generate a large data set of roadside images. For example, if the pipeline was being applied to guardrails, the data set would contain both images containing guardrails and not containing guardrails. These geotagged images would be labeled for the model to train itself on. After the data set was created, the data set would be used to train and test the model. The model would classify images based on whether or not they contained the road asset of interest. Once the model was trained, the results would be mapped. Markers would be created wherever the model indicated that there was a road asset of interest. So first, I'll be discussing my guardrail pipeline. To generate images, I used OpenStreetMaps and Google Street View's API. OpenStreetMaps is a map that contains coordinates of every single geographically significant feature, such as lakes or roads. I parsed OpenStreetMaps for the coordinates of the boundaries of every single road in a certain area. I then used this list of coordinates in Google Street View to create roadside images. I mainly focused on highways, where I knew there would be a high volume of guardrails. After I generated a large data set of roadside images, I manually labeled the images based on whether or not they contained a guardrail. On the right-hand side, you can see what some of these images look like. I was also generously provided a large labeled data set of 1,000 images by the KTC. These images provided by the KTC were generated in a similar fashion to the way that the Google Street View images were generated. They were created by a dedicated image capture van, and these images were used to train the model. After I finished generating the dataset, I had around 13,000 total images. Around 1,000 of them were from Google Street View, and the rest were from the KTC dataset. I used these images to test 3 different machine learning models: an AlexNet, a VGG16, and a ResNet50. Here are the results. In this chart, the validation accuracy on Google Images is displayed. I used different combinations of datasets and models to find the highest accuracy. The VGG16 trained on both datasets had the highest accuracy, so I used the results to map guardrails. The results of the VGG16 that were trained on both datasets were mapped on Google Maps. The model classified images based on whether or not they had a guardrail, and a marker was placed wherever the model indicated there was a guardrail. On the bottom, a segment of the guardrail map is shown. Each red marker indicates a guardrail. When tested, this proved to be accurate, as the locations of guardrails were consistently indicated with a marker. After the pipeline worked for guardrails, I worked on applying the pipeline architecture to stop signs. The first step was generating image data. I manually extracted stop sign images from Google Street View and labeled them. I also generated and labeled a significant amount of background images that did not contain a stop sign. By the end of this, my data set had almost 2,000 images. I used these images to train and test a custom 8-layer convolutional model. Because I had a relatively small data set, I created a custom model to combat issues such as overfitting. I implemented measures that would combat these issues, such as adding dropout layers or reducing the architectural complexity. After testing the model, it achieved an accuracy of 96%. After the model achieved a high accuracy, I mapped the results on ArcGIS. ArcGIS is a mapping platform that the KTC uses to create maps. I used the results of the model to create a marker wherever there was a stop sign. The marker had the coordinates on, along with a link of an image to the picture from which the model classified it. When I mapped the results, the maps were cluttered with inaccuracies and misclassified stop signs. In other words, there were a lot of points where the stop sign was identified by the model, but upon looking at the picture attached to the location, there wasn't a stop sign. It was clustered with more false positives than true positives. This was due to the infrequency of stop signs per mile of road. As you can see here are the results of the mapping section. On the left, we have an area of Palomar that was manually mapped. Each dot was checked for accuracy, so every dot on there is accurate and is accurate for that area. On the right-hand side, we have the same general area of Palomar that was mapped by the model. As you can see, each red dot with a slash through it is an inaccurate classified area. Each red slash represents a point where the model said there was a stop sign where there truly wasn't. As you can see, the map is cluttered with red slashes, meaning that the map is inaccurate. After this pipeline didn't work, I implemented some measures to try and fix it. I tried to increase the data set, which increased the accuracy to 97%. I also tuned the hyperparameters, which bumped the accuracy to 98.5%. These measures increased the accuracy of the model, but the maps were still clustered with inaccuracies. I then focused on selective data generation to help reduce the image load. Because I know stop signs only occur at intersections, I used OpenStreetMaps to find intersections and only generate images at intersections. However, this selective image generation didn't work, as the only images generated were from the backside of stop signs, which the model generally avoided. These modifications didn't work because they didn't address the core issue, which is something I'll discuss next. In summary, I created two pipelines to map road assets. The pipeline to map guardrails worked, and it demonstrated an efficient way to map guardrails from a publicly available data source. However, the stop sign pipeline failed. While every individual component worked, when pieced together, it created inaccurate maps that were clustered with false positives. This was due to the infrequency of stop signs per mile of road, a concept I've mentioned before. The best way to explain is this. Stop signs occur very infrequently per mile of road. Because of this infrequency, there might be up to 10 stop signs per every 10,000 roadside images. Even with a model that has 99% accuracy, this means around 100 misclassifications. As a result, you might get around 100 false positives compared to the 10 true positives that existed in the data set. With this in mind, machine learning models were not the best way to approach sign map creation. For future work, I would want to get the stop sign pipeline working. I would completely replace the image classification part with something new. Sign detection is something that should be based on shape and color characteristics instead of using a machine learning model. I would use sign-specific techniques to classify the images instead. Furthermore, I would apply this pipeline architecture to other common assets, such as median dividers. So, acknowledgements. I would like to thank my mentor Yang Song for taking me under his wing and helping me throughout this project. I would also like to thank the University of Kentucky and the Kentucky Young Researchers Program for providing me this opportunity. I would like to thank MSTC, Ms. Young, and my family and friends for continuing to support me through this research project. Right. Here are my references. If you have any questions, you can email me at evan.yang@stu.fayette.kyschools.us.